Um, Hello everyone, I'm Kilian Speiser from the Technical University of Munich, of Denmark. Very sorry, I studied there before. Um, I'm from the Technical University of Denmark, and I'm presenting my work with the title Work-Centric Path Planning that I pursued together with my supervisor, Jochen Teizer. To start out with, I want to show you an image of a construction site in Finland, a residential housing building, and we look into a more specific area where a situation occurs that is every construction worker faces many times a day. There's a pedestrian worker, they want to go to a location in the site, and they have different options to arrive there. For example, here, taking the ladder and going to the target location. But they could also maybe take the other path where they don't take the ladder because, in fact, ladders are relatively dangerous. But maybe take the blue path and avoid that. However, there is a traffic zone, and on the right you can see a wire. So this is also hazardous. So in fact, we want to find out while the yellow path is much shorter, which one is actually safer and how can we quantify that? While in construction safety, we have indicators for this. Most of them are lagging. And lagging indicators means that we have accident data, but this is all about accidents that have already occurred in the history. And we are interested in indicators where we can predict, so where we can have leading indicators to see how hazardous different paths are. And in this research, the objective is to find the safest route for construction workers. I will introduce some relevant background. First of all, graph theory, where we can represent different concepts with knots and edges. In this case, coming back to the example from before, we put some knots in the side, connect them with edges, and then we can use pathfinding algorithms to find the optimal paths. Where mainly we equalize optimal with the fastest, but as I said before, we want to find the safest path. And for doing this, we need to associate a cost with each of the edges. And right now there is no such obvious cost that we can assign. And this is where I introduced the second concept, hazardous energy, which goes back to 1968 already, where Haddon claimed that the consequences of incidents should be defined by the release of hazard energy. And quite recently, Matthew Hallowell then investigated 500 accidents, and they found out that there is a high correlation between the hazardous energy and the consequence of an accident. To illustrate this, I have two examples. You can see on the top image, there is a construction worker under suspended crane load. And depending on the weight and the difference in height, this is approximately 60,000 joules that could then hit the worker. On the bottom, the worker approaches an object and they could trip. In this case, roughly 300 joule. And there's a big difference. While most likely the first one would result in a fatality, the other one is what we call a low energy hazard, where if it's unfortunate, there could occur an injury, but probably there is no consequences of this incident. Using these concepts, we come up with a novel graph structure to quantify hazards. And in this study, we propose a method where we create a synthetic environment in the game engine Unity and model typical hazards, in this case falls and trips, which amount to a large number of accidents in construction sites. In the next step, then we instantiate knots for each location in the construction site. In this case, we used 1 meter squares, but it could be much less or was also more. And in the next step, then simulate the hazardous energy. While I think the first two pictures here are quite explanatory, I will delve a bit more into how we get the hazardous energy. And for that, we look in one of the knots. I mentioned there is a construction worker. Now they have different options to move to the adjacent fields. And when they go to, for example, D, there wouldn't be any hazard on the way. But to C, they could trip over the cement bag, and to E, there is an elevation difference, so they could potentially fall. And these numbers show the hazardous energy in joule. We then run the same in the simulation in Unity for all the knots. In this flow chart, you can, what I just described in words, see how it's finding if there is any hazards on the way when they move from one field to the other. And I show here a quick animation how this then looks like. For each of the motions, in this case it was 1024, we calculate the hazardous energy and add it as a cost to a graph, which is then exported so we can analyze it. So now you can see there's, for example, this material on the ground, and this is a potential trip. So we add an edge with the cost of this hazardous energy. The final graph is then used, but now we may wonder why is it, what is it useful for? What's the purpose of this graph? And there are several applications that we could envision. But first I want to highlight that there's a very good, or why did we choose a graph is, for example, and we don't need to run the simulation all the time once there is a change in the field, and construction sites are highly dynamic sites, where, for example, now if we move an object, we don't need to rerun the whole simulation. We can just update it locally. Like here, that bag is removed, then we just update the edges that are connected to this bag, cement bag. But as I said, there are several applications. In this case, we want to illustrate it in a virtual setting. We envision that the worker in the field could get provided the optimal path that we calculate. But also we want to use it to compare construction workers when they choose routes, how safe they were. So imagine there is a starting node and a target. And then in a virtual setting, we ask users to navigate in the site and try to find the safest route from one place to the other. We did this with multiple users. I only show now the result of 2. The first one takes a quite deviative path to the target location, trying to avoid all the hazards in the scene. And the second one in purple, they take just the shortest straight down, but it's much faster. But as we see now, in the hazardous energy, which you can see on the table of the right, the purple, they were exposed to much more hazards. In a quantitative measure, here 2,200 joule, the first one 1,500. And in this graph, we can also use path finding algorithms for finding the optimal path, so the lowest energy. And we can also compare now how well did one of the trainees perform compared to the optimum. And maybe I just should point out the blue one here is one optimal path. There are others, and these pathfinding algorithms always find the optimum, but it's just one option. So with this example, we illustrate that we can use our graph to find the safest path in a construction site and also compare performances of different workers. To conclude, again, I want to point out that this novel graph structure quantifies hazard energy potentials in a virtual construction site, where we also would like to test it in a real construction site. And it can suggest safer working routes. We want to further enhance the simulation. First, introducing more different kind of hazards. As I said before, it is limited to falls and trips. And also we want to make it more dynamic by introducing maybe equipment that moves while and then find the safest path. The future work, beside these enhancements on a higher level, we want to introduce it on a real world validation, and then also check if we can apply it in a high energy control assessment, which is a new approach introduced some last year. It's a leading approach to evaluate how safe are construction sites. And yeah, maybe we can also use this safety graph concept in the context of this. Thank you very much. And again, I'm from the Technical University of Denmark.
Thank you so much.